In physics, when we look at projectile motion, there's really two main types of problems. And one of the first problems we're going to go through is something called a cliff problem. Now, this is a sense where we have something that is moving off of a cliff, and it's going to travel perfectly horizontal with some initial velocity. Now, that velocity is going to be in the x direction. So we're going to start in breaking up motion in terms of x and y, with x designating horizontal motion and y designating vertical motion. So, and we do that because these two types of motions are actually going to not impact one another. So there's no relationship between the x and the y. And so we are going to look at them as separate types of motion. Now this object, when it rolls off of a cliff, is going to take a path that looks something like that. What's going to be true is that x velocity is going to stay the same throughout. So that x velocity is going to not change. That's a constant velocity. So x motion is constant, and then the y motion is going to be accelerated. Okay, so with the y motion, initially the y velocity is 0. But then as it travels, because gravity is pulling it down, the acceleration is going to cause that velocity to increase in the y. So our y velocity is going to get bigger and bigger and bigger. So we're going to deal with these motions as two separate types of motions. Because x is constant, our velocity is going to stay constant. That's not going to change. There is no acceleration, so s and then t. Now, I'm going to draw this like this. So this is our main table of information that we're going to get for this. Okay. S would be kind of the length of where it hits the ground. How far away from the cliff is it going to hit the ground? We'll call that sx, so that's in the x direction. And then the ys would be this, the vertical height that it travels. So in my vertical motion, my y motion, I'm going to have an initial velocity in the y direction is 0. Because this is not launching up or down, right? We're not launching it this way or this way. We're going to say that the initial velocity is simply 0. I know my acceleration is going to be a -10 or -9.8. I know sy is, what that is there. And then time, we need a little bit more room over here. Velocity, when it hits the ground, that's going to be this velocity there. So that's velocity y final when it hits the ground. That's going to be based upon how high it's going to be falling from. Okay, but the one thing that I can take back and forth is time. Time is the same for both the x motion and the y motion. So oftentimes in these problems, what you're going to have to do is, if I am looking at how far something is going to land from the edge of my cliff, I need to know how long is it going to be in the air for. Well, I can do that using my acceleration motion, right? So I could say, let's do this. There we go. So we can say kind of time in air. I could find from my y motion, I would use s equals initial times time plus 1/2 at squared. My initial is 0, so that whole first part of my equation goes to 0. And so I'm just going to have sy equals 1/2 ayt squared. If I solve for t, that's going to be 2 sy divided by a, and t would equal that, the square root. All right, so that's a way that I would find my time in the air. And then if I want to find, how far from cliff, I can use my motion in the x. And the only equation I'm really going to be able to use is the idea that the distance equals velocity times time. This is going to be a constant velocity, and then the time in the air. And so I could basically, whatever I solve for here, I can plug that back into here and solve for how far it's going to be traveling, right? The last thing then that someone might ask is kind of the total speed when it hits the ground. And this is where vectors are going to come into play. Because when it hits the ground, let me zoom back in here. When it hits the ground, it's going to have both an x and a y velocity. So I can solve for my y velocity just like something free falling. And then to solve for how fast it's actually traveling, I'm going to need to add these vectors together. So to do that, I would add them head to tail. And again, it doesn't matter which way I add them, right? This would be Vy, or I can move Vx down here, but I'm going to add those two vectors head to tail, Vx, and then my total would be there. So this would be my total velocity when it hits the ground. And if I look at this, you know, if I know the velocity in the x and I know my final velocity in the y, I can do simply Pythagorean's theorem, 90-degree triangle there, to solve for my total, right? So the total speed when it hits the ground, then I can say, okay, well, that is velocity in the x, because that's constant, squared, plus velocity in the y final, right? Squared, so right before it hits the ground, equals velocity total squared. So velocity total, not squared, but equals the square root of my velocity in the x squared plus my velocity in the y final squared. So that's how I'm going to solve for that. And if I needed to know the angle, I could just use the idea of vectors again in solving for this angle there. But that's a cliff problem, and that's very similar no matter what. And a cliff problem is very specific in that essentially it's velocity, initial velocity in the y is going to be 0. That's what I consider a cliff problem. Everything else would be a rocket problem, but that's for a different video.